Okay, hi folks. I was planning to make my previous segment a little bit longer, but I ran into some technical difficulties, so it ended up being only 14 minutes. So hopefully this segment two is going to be a bit longer. All right. Last thing that we did, this is a quick review from what was done in segment one, is that we took a generic element, a spring element, so with a stiffness Ke and masses at the ends, the left mass and the right mass, and displacement XR, force FR, displacement XL, force FL, and using the equation of motion, I wrote the using Newton's second law, I wrote the equation of motion. So let me quickly write that thing down. It looked like this: ML XL double dot plus KE XL minus KE XR equal to FL, and MR XR double dot plus KE XR minus KE XL equal to FR. I wanted to write this thing in a slightly more compact form, so here's the way I'm going to do it. A 2 by 2 matrix, ML, 0, 0, MR, times the acceleration vector, XL double dot, XR double dot, plus a 2 by 2 matrix, which looks like this, KE minus KE minus KE, KE, times the displacement vector XL XR equal to FL FR. Notice that this is a very nice compact form. This is called the mass matrix. This is called the stiffness matrix. This is the acceleration vector. And obviously, this is the displacement vector. And finally, the thing on the right is the load vector. Of course, these are all at the element level. All at the element level. Now, there's certain things that we can observe here, and that is, first of all, in the mass matrix, the masses appear only on diagonal line. This is why it's called the lumped mass matrix. And then it's nice and symmetric, by the way. And the stiffness matrix is also symmetric. Also symmetric. And remember, symmetric matrix is one where the transpose of the matrix is the same as the matrix itself. By the way, there's a lot of linear algebra involved in finite element analysis. Now, you don't see it as an engineer, you don't see it as when you use it as a black box, but those poor people who wrote these codes, they had to know a lot of linear algebra, and that's why you took a linear algebra course in your first year. It was not done for no reason. In any event, now this is all at the element level. But remember, our objective when we go to our original problem, the original problem involved 3 masses and 4 springs. I don't want to go back to the diagram here and show you what it was, but you can go back to segment 1 and see what the arrangement was. And remember, the unknowns were x1, x2, x3, x4, x5. Now mind you that these are 0. These are the displacement at the wall, and there is reaction forces at the two walls. Now, there is 5 displacements. And this is why it's called a 5-degree of, it has 5 degrees of freedom. So in principle, you need to say something about these 5 unknown displacement, and at the end of the day, you want to get a mass matrix involving accelerations, the 5 of them, x, this is x2, this is x5, these are the acceleration, plus a stiffness matrix, this is the global mass matrix, this is the global stiffness matrix, times the displacement vector, x1, x2, all the way to x5, equal to some load, or global load vector. This is what we want to get by looking at these elements one by one, somehow transform or superimpose, let's think about us superimposing those 2 by 2 matrices and those 2 by 2 displacements and acceleration, etc., in this 5 by 5 global mass and stiffness matrices. And this process that I'm going to be describing to you is going to be called assembly process. Incidentally, very frequently people write this thing in an abbreviated form. They write the mass matrix times the global acceleration vector plus the stiffness matrix times the global displacement vector equal to some global load vector. All right, so here's what we're going to do. One by one, we're going to loop through the elements, write the equilibrium equation. Okay, let's see now. Let me see. This is where I ran into problem last time. So I want to insert a blank page. Why does it? Okay, I think I know what the issue is. So we go here, go to the end, insert a blank page. Okay, good, good. So let us loop through the elements. Loop through the elements. Write the equation of motion. For each. And then put it in the right spot. In the global equation. Okay, so let's look at element number 1. And I will leave it to you to go back and draw that original drawing that I had for you. It's a good idea if you don't have it in front of you right now. go back to segment 1, get that drawing which looked like this. That it is important that this thing be in front of you while I'm going through this discussion. I ended up drawing it anyway, so that's fine. Sorry. So this is going to be element 1, element 2, element 3. I was trying to avoid doing this, but too late. 1, 2, 3, 4, and 5. Also keep in mind that the force, there was a global force here, F. For now, we're just going to totally ignore these global entities that eventually we have to put into place. So, element number 1. So how does element number 1 look like? You just look at this. There is my element number 1. In principle, I can view it as a spring with a stiffness 1. Here is, well, let's think about it as this is node number 2, and this is node number 1, or mass 2 and mass 1. Or I can think about this thing as I can think about this thing as having a left mass So this is my left mass, and this is my right mass. Okay. So how does the equation of motion look like for this? So it comes like this. There is a left mass, and you're absolutely right in saying that, wait a minute, what left mass? This is the wall. So for now, just pretend that the left wall, which doesn't move, is your left mass, okay? And there is right mass. There is L, X, R, these are accelerations, plus stiffness, K1, okay, because we are dealing with element 1, K1, and this is negative K1, K1, times the acceleration vector, times the displacement vector, XL, XR, equal to the load vector. Now, first of all, I am going to put a superscript 1 here because we are dealing with element 1. On top of the m's, notice that I put a superscript 1. Also, the load, which is always a left load and a right load for any element, I'm going to put a superscript 1. This is to emphasize that this left force that I'm talking about and the right force that I'm talking about is from element 1. So if I wanted to add these things here, that'll be FL1. Obviously, this is XL. And this is F right 1. And here is your X right. Okay? Now, you do realize that this can also be viewed. Your left is associated. This is left local. When I'm looking at this generic, is associated with node 1, global. And the right local is associated with element 2. This observation is important because it tells you where in the global equations this 2 by 2 matrix is going to go. So here is what I'm going to do. I'm going to put your global equation. We go to the end of the page. Okay. And put my global equation. So that means I have to move this now. Okay, this is. Let me see how I can move this up. Man, this is a mess. Okay, so You know what I'm going to do? Let's see. I want to move this down. Ah, there. Okay, excellent. All right, so that 2 by 2 matrix is going to go in here. So when you think about it, let me, making a video is a lot harder than what I thought. So there it is. So we have M1 left, 0, 0, M1 right. And then minus K1, K1 minus K1 minus K1 and K1. And here you're going to have F1 left and F1 right. When you look at this, it's exactly the same 2 by 2 matrix, the matrix equation that I wrote down, except that I've now put it in the right spot in the global equation. Good. So now we're done with element number 1. We have to loop and go to element number 2. So now element number 2. Remember I said we're going to loop? All right. So let's do element number 2. And I'm going to draw it for you. So element number 2, when you think about it as a spring element, well, it's always a left one, left mass. And there's always a right mass. So this is your right mass. This is your left mass. This is for element number 2, which has stiffness of K2. But remember that this corresponds to global node number 2, and this is global node number 3. I don't have to draw it on this diagram, but anyway, I decided to do that. So here we have the force FL, but from element number 2, and of course the displacement left, which happens to be x2. And there is your FR, which comes from element number 2, and there is your XR. All right, so how does the equation of motion look like? And by the way, this is your M left mass from element number 2, and this is right mass from element number 2. So the equation of motion for this element becomes M L M R from element 2. There's a 0 here and there's a 0 here. XL double dot, XR double dot, plus K2 minus K2 minus K2 K2 2 by 2 matrix times displacement XL XR equal to FL, always FL, always FR, but coming from different elements. All right? And I want you to see that what happened here is that we have a local labels and global labels. The local label is always left or right. And the global label for this particular element is 2 and 3, which tells us where in the stiffness, global stiffness matrix and mass matrix these things are going to go. All right. So now I'm going to see if I can I copy this thing? Let's see. We still have time for this segment, so let me see if I can select this region. Okay, good. Copy. Well, actually, you know what? Maybe I do it like this. Copy, Let's go down here and paste it, and there's some junk here that I'm going to get rid of. For example, this stuff. Okay, so let's go to, I'm going to go to the next page now. Insert. Good. So this is all the, yeah, good, good, good. So where is this stuff going to go? I'm going to use a different color. So let me switch to, say, red. So there's going to be a plus m left from element 2, a 0, a 0, m r element 2. These are not squares. This is not the square of ml. It's the from element number 2. And then plus k2 minus k2 minus k2 plus k2, which I'm going to just leave it as k2. And there's going to be plus fl and fr, but from element number 2. And you can see why I'm using these superscripts, because they may have occurred to you that, wait a minute, I don't need those superscripts. But you can see that when they're coming from different elements, we have to treat them differently and eventually come and clean it. All right. So now we go to element number 3. Remember, we have to loop through these things. Element number 3. And how does it look like? Well, element number 3 is also a mass spring. Looks like this. This is element 3 with a stiffness K3. This is ML, always a left one, but from element number 3. This is always the right mass, but from element number 3. The displacements are X left, X right. The forces F left, but from element number 3, and F right from element number 3. And keep in mind that these corresponds to globally node number 3 and node number 4, and this will tell us where in the global equation these are going to go. Now I have to do a cut and paste from the top, that matrix on the top, bring it down here. Since I'm going to run into problem, I'm going to stop the segment number 2 here, and we start another segment number 3, where this 2 by 2 equation is going to go in the right spot. Maybe I still have time to write the equation at least for you. So let's go and do that. So here's the situation. The equation of motion is ml, mr, 0, 0, but coming from element number 3. Remember, this is not cubing ml. It says that it's the left mass from element 3 times the acceleration vector, always xl, always xr, double dot, plus the stiffness, K3 minus K3. Remember, this is a 2 by 2 matrix. Okay, minus K3, K3. Displacement, always XL, always XR, X right, equal to element load vector, always FL, FR, but with contribution from element number 3. And this is going to go into that matrix. Do I have the time? Yeah, I have the time. So let me go here and copy this. Copy, bring it down here. Yeah, let's go to the next page. Gotta insert the page here and paste. Okay, so let's put it in there. I'm going to use a different color. How about maybe green, and assemble. So there's going to be plus ML from 3, 0, 0, MR from element number 3 plus K3 minus K3 minus K3 K3 plus FL from 3 FR from 3. Now I can do quickly the last one for you. Okay, so for element number 4, without drawing the actual element for you, generic element, I'll just write the equation of motion. So it's going to be ML, MR, but these are from element number 4, XL, XR, from element number 4, of course, plus K4 minus K4 minus K4, K4, time displacement equal to FL, FR, but these are coming from element number 4. And we can now put it in the right spot down below. I'm going to do a instead of, well, okay, let's copy this thing. That's okay. Copy. And paste. All right. Yes. Okay, so it's going to be, put it in the right spot. Plus ML 4, 0, 0, MR 4, plus K4, minus K4, minus K4, K4, plus FL from 4, and FR from 4. I'm going to stop the segment here and start from this point on and see what needs to be done. Let's stop.